Welcome everybody to the August 2025 meeting of the Mornington Peninsula Astronomical Society. And as usual, a couple of things to mention here. I'll start actually at the bottom, showing on the screen there. At the bottom left, there was reports of a meteorite that had punched its way through a house in Georgia. This is Georgia in the United States. And you can see them holding up the size of that meteorite. It came down about 1 o'clock in the afternoon, and it was picked up by lightning detector satellites of all things. So they actually saw it come in. Apparently those on the ground said it was as bright as the sun, and the Earth was shaking with it all. And when you actually look at the meteorite, either that's a tiny fragment and the rest of it landed somewhere else, or someone was sort of embellishing the story a little bit with that one coming in. But they do occasionally damage houses and damage cars, and you do get to see those on the news sometimes. Moving across to the bottom one in the middle, NBN here in Australia has confirmed that they're trading in their old satellites, which are out at geostationary orbit, so they're a long way from the Earth and they stay in the one position over the Earth. They've got two of them that they call Sky Muster, and this is how NBN delivers its services across the country. They're trading those in for Amazon, who's putting up a constellation of low Earth orbiting satellites. There'll only be about half the number of Starlink with Amazon, because apparently the technology is a bit better. And so they're replacing those two satellites that stay in position with 3,200 satellites that go skimming across the sky and ruin the night sky for all the astronomers. At the moment, as of today, Starlink has just over 8,000 Starlink satellites up in orbit, and they're aiming, at least in the first rollout, of 42,000. So they've got 8,000 so far, so if you think that's bad with any night sky photography that you do, just wait till they have 42,000 up there and you'll know all about it. Down at the bottom right, we've got the Mars Society setting up a test habitat here in Australia. They've got one set up in an island near the Arctic Circle, one in the middle of the Utah Desert and one in the Himalayas already, and this fourth one is going to be in outback South Australia in Arkaroola. And this is to try and simulate the protocols and how people actually live in a confined environment where they can't easily go outside. So very much a test bed before they leave the safety of the Earth. Now we go up to the top left-hand side, and since we last met, I'm not sure if any of you have heard the name Tom Lehrer before. He's a Harvard mathematician and songwriter, and famous for the so-called Element song. That if you've never heard that one before, we will play the updated version of it at the end, because he died at the age of 97, but a few years ago he actually signed over all the songs, all his books and everything to public domain. So it's they're freely available to everyone to use. But his one only went up to a certain number of elements of the periodic table that were known at the time of 1957, I think. And obviously we've discovered some more elements since that time. To the middle of the top row, shown there is Fred Espenak from NASA's Goddard Space Flight Center. He passed away back in June. He's the one that's usually affectionately known as Mr. Eclipse, because if ever you've been to a solar eclipse or lunar eclipse, you've actually looked at his predictions. So he's done, he published a great big 5,000 year canon of all eclipses from 2000 BC up to 3000 AD, which covering all the solar and lunar eclipses anticipated. And unfortunately for him, he died of pulmonary fibrosis, which is like a scarring of the lung, and they weren't able to get a replacement lung for him in time, sadly enough. So he'd actually attended 20 solar eclipses in his lifetime, so he was well and truly into eclipses. And then on the top right hand side we see Jim Lovell there, who's one of the Apollo astronauts. And he also passed away a few days ago on the 7th of August, aged 97, so he lived to a good old age. And he flew on the Gemini 7 and 12 missions, which were precursors to Apollo, and also the Apollo 8 and Apollo 13 mission. And Apollo 8 was the first one to go around the moon, so he holds that honour with the other two members of the crew. And also he was on the ill-fated Apollo 13 as well. And in the movie Apollo 13, he was the one that Tom Hanks plays. And in light of that, I will just play a couple of minutes video.
Jim Lovell is one of only 3 men who's been to the moon not once, but twice. And that's not all that's fascinating about his career. In my opinion, he is one of the most interesting Apollo-era astronauts. And while I'm traveling right now and cannot make a regular video, I do have access to a ton of B-roll from his flights, so I thought we would go over a few mission highlights to mark his passing. So Jim Lovell's story starts with the Mercury selection process, which he, of course, did not make it through. He was not selected as one of the original Mercury astronauts because his liver had an excess of bilirubin. Bilirubin is a yellowish substance found in bile that is produced by the breakdown of red blood cells. It has nothing whatsoever to do with spaceflight, which is why he was then selected as part of the new 9 in the second group of astronauts. His first flight was as the pilot of Gemini 7, which is a really fascinating mission. Gemini 6 had a launch abort, so NASA made the decision to launch Gemini 6A at the same time as Gemini 7, which meant that this was the first time 2 spacecraft actually flew independently at the same time on a mission. His flight, however, was the duration of the 2 missions, and he and Frank Borman were up for 2 weeks, and he did say that it was a little bit on the grueling side. His second spaceflight was Gemini 12. He was the commander this time around with Buzz Aldrin as his pilot, and this is a really interesting mission because it was, of course, the last of the Gemini missions. This was the one that kind of brought everything together. Gemini was the proof of concept, proof that NASA could actually do things, live and work in space, and everything had to be done on Gemini 12. His next mission was Apollo 8, the first human mission to the moon over Christmas in December of 1968. He was the command module pilot on that mission, which is why in so many of these shots from the flight, you can see him doing navigational exercises. And of course, his last mission was Apollo 13. I'm actually working on a super deep dive into Apollo 13 right now, but everyone knows the basics of the story. A little under 56 hours into the flight, one of the oxygen tanks ruptured and effectively crippled the main spacecraft, the command service module. That left a crew of 3 with only the lunar module for life support, a vehicle designed to take care of 2 men for 2 days, not 3 guys for upwards of 4 days. These 4 missions are 4 of the most interesting and also historically important missions when we're talking about the history of spaceflight and also looking at the space race, which is why I think it's fair to say that Jim Lovell has one of the most incredible careers of any astronaut.
Okay, so for tonight we'll start with the welcome and any new members. We'll welcome everyone to the Society, and in terms of new members, do we have any Nerida? We have a couple up the front here. Welcome to our monthly meeting for members, and I'll get any committee members here to put up their hands so you'll know who to approach afterwards if you wish, and they'll gladly show you around, as will I if you come and say hello to me. We'll look at the events over the past month and the coming month, and it's certainly been a very busy month with National Science Week on. Then I'll throw over to Chris for Astromofo, and he's got a bumper edition tonight. Sky for the Month by Guido. Guido's currently in Scotland at the moment for work, so he's sent us some slides, and I will try and do my best to decipher the Scottish accent on it and give you a sky for the month. Then we'll look at From Apollo to Artemis. This is 2 shorter talks, one given by Harrison Schmitt, who was the last man on the moon and the only geologist to ever visit the moon. This is a talk he gave about the geology of the moon back in 1973, and then it's followed by a more recent one by Dr. Giulia Magnarini from the Natural History Museum in London, who's also an expert in lunar geology. Then we'll look at whatever happened to the missing Apollo numbers. As you know, there's an Apollo 1 and then it suddenly jumped to Apollo 4. What happened to 2 and 3? And also what about the ones that never launched? Where were they going to be going? So 18, 19 and 20 were already built, although they never flew. and then we'll close with the updated version of the Elements song. All right, so recent events, very busy slide here because it's been a very busy month. The background photo there is by Sylvie of the Hong Kong visitors that we had the other day. They're the one right at the bottom of the talk, the most recent one, right at the bottom of the slide. So we begin at the top there. On 19th July we had the Cosmology Discussion Group, Working Bee, and Dr. Tim Patson gave a talk on Indigenous astronomy. I wasn't able to be there myself, but it had a great turnout of 40 members. Unfortunately the cloud wasn't too cooperative that night. Then we had a committee meeting a few days later, followed by the Skag night, Scout Cubs and Guides, when we had the Devon Meadows Cubs and Somerville Cubs as well came here to the Briars. Again, unfortunately, it was very cloudy that night. The public night with Guido was a little bit better. We had some clear sky to see. Then we had Glenferrie Primary School, who were staying next door at the camp. They came on over, 76 of them, and we gave them a talk, and that was a bit cloudy, but they were able to see some things. Some members went across to Vastrock in Geelong. They were able to get there on the Saturday, on the 9th of August, and then the next week we were full on into Science Week. We had the big Cornish College out near Patterson Lakes, Bangholm. We had 150 there that night of pretty much all except for their very youngest grades, and they had a wonderful night. In fact, they've already asking for us to come back same time next year at this stage. They were so impressed. A couple of days later we were out in the public park at Chelsea Heights Community Centre, and we didn't have any cloud to contend with, but there was plenty of light from the football field that we had to wait for them to turn those lights out before we could do anything useful. 14th of August, the next day, we were down at Balnarring, and we had 245 for that one. Their initial estimate, I think, was 150, and so they had one or two extras, and all at the last moment, I might say. So the parents and siblings and anyone else decided they wanted to come along and hear us as well, so they filled up the hall. And they had no cloud as well, so they had a very, very good night. 15th of August we had the second public night because of Science Week, and there was only a tiny bit of cloud here. Trevor gave the talk, and then the final one, the visitors from one of the Hong Kong primary schools came here to the Briars, and two big coaches turned up with them, and they had a ball of a time. They absolutely loved it with no cloud here. So coming soon in the upcoming month, this Saturday, there's the Working Bee and Member Barbecue as usual at 4 o'clock. Then there's another Indigenous astronomy talk by Dr. Dwayne Hummaker that Chris has arranged to come down from Melbourne University to give us a talk. You're all welcome to attend that one. It'll probably be somewhere around about 6 to 6:30 time, I imagine, depending on when the barbecue finishes. Next committee meeting is next Tuesday, which will be by Zoom. Next Saturday, the following Saturday, is the Cosmology Discovery Group here at the Briars on the Saturday afternoon. And then the following Monday and Tuesday, we've got two groups from Toorak College. They usually come in by coach as well, or alternatively, if they're next door at the camp, they'll wander over. In this case, there's going to be 66 Year 7 girls on the first night and 44 on the second night, different classes. Then the public stargazing night for September, which has already been well and truly booked out. Guido should be back by that stage, and hopefully able to give that talk to the public. Chris will say more about the astrophotography workshop, so I shan't mention anything more about that. And then obviously this meeting next month is on the 17th September.
Welcome to AstroMofo number 25. So for the new people here, AstroMofo is a monthly photo challenge that we do here at MPAS, and every month or every 2 months, depending on my availability, members are charged with taking photos of on a particular topic or a particular object. And the last challenge was for members to compare their images with images of their object taken by Hubble or the James Webb Space Telescope, and just compare how they compare. And the first image that we've got here is one by Stephen Moore of NGC 1512, a barred spiral galaxy. And just in case you're not sure, the Hubble image is on the left and Stephen's image is on the right. So pretty nice comparison there. This is Stephen's first contribution to AstroMorpho, so it's not a bad photo for a first timer. Okay, this challenge was completed by Stephen Moore, Fred Prater, Greg Walton, Nick Axaris, Russell Smith, Steve Wilkins, David Rolfe, Dennis Cook, Dominic Lucarelli, Mark Stevens, Michael Barrow, Neville Drake and Sylvie Grandit. The ones with the star are first-time contributors for this year anyway, not necessarily overall. And this image we've got was sent in by Fred Prater of M20, the Trifid Nebula. And you can see the squared in part is of Fred's image is the zoomed in part of the Hubble image, so you can get a bit of a comparison and of the difference in resolution. Although it is hard to actually compare the resolution difference in these images, because unless you actually get the full Hubble or James Webb image on your computer, you won't appreciate how much detail you can actually see in them. But well done to everyone for completing this challenge. Okay, this is another one. We'll go through Stephen's images first, just to show us all how incompetent we are. And this is of the Eta Carina Nebula. So this field of view is around about 26 arc minutes wide by about 16 arc minutes high. For those of you who don't know what an arc minute is, you've got a circle is divided into 360 degrees. Every single one of those degrees is then split up into 60 arc minutes, and each one of those arc minutes is divided up into 60 arc seconds. So this is 26 arc minutes is a little bit less than half a degree. So if you're looking up in the sky, angle about half a degree, that's a sort of area this covers, which is actually, you might think it's small, but it's actually not that small, because the moon is actually around about 32 arc minutes in diameter. So 26 is just a little bit smaller than the full moon. And just as a comparison, the Hubble field of view of a single image of the Hubble is only about 3 arc minutes wide, 3.16. It's around about 10 square arc minutes is a single shot of the Hubble. So this is a composite image taken of quite a few images across and up and down, and it's mosaiced into a single image. So if the Hubble was to image the full moon, it would need to take around about 11 shots across the full moon to create a full image of the full moon all the way across. Now I've just got a couple of comparisons here. So that's Stephen's image on the top, and below are some of the Hubble images. So I've flipped the image from what it was previously, just because that's the order they appear in. We've got Mystic Mountain on the bottom. You can see, might get my pointer out. Okay, Mystic Mountain is this object here, and it appears in Stephen's image over here. The next one is next to the Keyhole Nebula. So the Keyhole Nebula is this section of Eta Carina Nebula over here. And in the Hubble image, you can see that there. And there's also this feature here, which is called the defiant finger, because it looks like someone doing that. So I censored it for you because we're a family here, but looks like someone, being very defiant. And then we have also, to really illustrate the power of the Hubble telescope, that's the star Eta Carina there. And if you have a close look at it in Stephen's image, it looks a little bit elongated, but then the Hubble is actually able to zoom in to that to show the actual resolution of what is called the Homunculus Nebula around the star Eta Carina. So what that is I think it was around about 1840, Eta Carina had an outburst. It's a multiple star system, and then interactions between the two stars called an outburst, like possibly a nova, which was recorded at the time. And what we're seeing in the Homunculus Nebula is the result of that nova, with material being thrown out during the interaction between the stars in the system. So yeah, some great details there in Stephen's image, and then below we can really appreciate the power of the Hubble telescope as well. Another one, this is also part of the Eta Carina Nebula, which is called the Gabriela Mistral Nebula. And this feature here is known as the Cosmic Cliffs. So we've got the Hubble image above and then Stephen's image below. And just as an idea, this is also a pretty popular astrophotography target. It's a reasonably bright object that can be imaged. And that's pretty much the whole Gabriela Mistral Nebula and that feature highlighted there. So it's, Gabriela Mistral is just, that's the other bright section on the right there is one of the lobes of Eta Carina Nebula that you can see. And that image is actually, I've just noticed, on the back wall over there, if anyone wanted to have a closer look at it, just on the bottom. That's the one. Okay, next we've got Stephen's image of, and like I said, these aren't bad for a beginner, but the Helix Nebula. So Hubble on the left and Stephen's image of the Helix Nebula on the right. Helix is also visible by eye through a telescope or through a decent set of binoculars. When it's up in the sky, you can actually see the shadow of it and the shape of it through a telescope. You won't see the colour, but you can make it out. Then we have the Trifid Nebula, and Stephen's photo on the left there, and then he's pulled out a detail. So Stephen's detail is the pink image on the right, and the Hubble image is on the left. So again, the Hubble image, even of that small region in Stephen's telescope, which is a fairly powerful telescope. It was around about 2.5 metre focal length, or about a 2 metre focal length, I think. Similar field of view to the Meade that we have in the observatory. And it's able to see that. But even that photo there by Hubble is also a mosaic made up of multiple images. And that's why we have these jagged edges on the Hubble images, because they are mosaics and not all the parts are always filled in. The Lagoon Nebula as well, which I think is also on one of the walls here by Stephen too. And again, he's picked out a detail of that to compare to. So the Stephen's detail is on the right, and let's have a look. I'll just try and point the region that it's to. It's around about this part. Oh, there we go. That part there that I'm circling with a pointer now. That's the detail that we're seeing in the close-up view. And if anyone's interested, I think Stephen might be selling that telescope. So if you're looking for some new equipment and you've got a bit of cash lying around, you're trying to decide whether to put a deposit on a house or buy a telescope, you may want to consider. And then we have Pillars of Creation, which is a very popular target in the Eagle Nebula in M16. A lot of people are able to image this because it is quite bright. It's quite easy to photograph, and you'll see quite a few images of it coming up. So, Sombrero Galaxy as well. Hubble on the left and Stephen's image on the right, and that's the full image by Stephen as well with the Sombrero Galaxy, the tight crop. So if we go back, we're sort of able to see quite a bit of detail in both of those shots. But again, deceiving, because if you were able to zoom into the full Hubble image, you'd get a lot more detail than you can just see on the screen there. Okay, Dominic Lucarelli does some great planetary imaging, and he sent in this one of Jupiter. So who wants to guess which one is Hubble and which one is Dominic? Forget the top, it doesn't compare, it doesn't indicate, but who reckons the one on the left is the NASA one? No, who reckons the one on the right is the NASA one? Yeah, you're right, okay. All right, so it is visible. Okay, so these were taken around about 14 months apart. So you can see, I think it's Europa there in the Hubble image, the moon Europa coming around Jupiter. And you can see just over the course of 14 months, I mean, the resolution detail is obviously obvious because you all picked it. But you can also see the difference in the cloud patterns that occur in Jupiter as well over the course of time. So it's an interesting target to photograph because it does rotate fairly quickly. So even over the course of the night, if you're taking photos, you can do a bit of a time lapse of it slowly rotating, but then also the weather changes on it and you can just see different patterns change over the planet over time as well. Okay, David Rolfe sent in this photo of the lagoon and the Trifid. So again, we're able to make out the Trifid detail over here and compare that to the Hubble image. And this is in the Lagoon Nebula. The only problem is I couldn't figure out where in the Lagoon Nebula it is, but it's one of the brighter sections, and I think it's up around there somewhere. So Hubble really able to get that detail. We've got a few of the Andromeda sent in by Sylvie and David for comparison with the Hubble image. And this is the Hubble image I've found of Andromeda. And this image here took about 10 years to create. It is a mosaic consisting of around about 600 individual overlapping Hubble images. And the apparent diameter of Andromeda is about 6 times bigger than the full moon. So it's actually quite a large object. And yeah, 600 individual Hubble images to make that, and we can see some pretty good detail in the Andromeda galaxy using that instrument, so quite impressive. Sylvie sent in the Rosette Nebula for comparison, and we've got the dark clouds near the middle of the nebula to compare to Sylvie's image. And that region is, I believe, just around about that area there in Sylvie's image of the Rosette. That's taken with a small telescope, a Red Cat 51, so nothing overly powerful, but it gives us pretty good detail of the Rosette and something to compare to with Hubble. M20, these ones were sent, these are C-star images by Mark Stevens and Michael Barrow. And Michael sent in for comparison, a fairly new image of M20, and it's the one taken recently by the Vera C. Rubin Observatory, the biggest camera in the world, and we're able to see a lot of background stars in comparison to these two photos, and a lot more of the reflection nebula around there as well. Mark Stevens also sent his Eta Carina for comparison, and we've got some more detail picked out there against Hubble, although I'm not sure that we could find this detail in Mark's image. It's probably a little bit too removed. Neville Drake sent in another Vespera too, so it's another one of those smart telescopes, the Vespera, of the Eagle Nebula and the Pillars of Creation. It's a popular, like I said, it's a popular object, this one. Fred Prater sent this one in as well of his capture of it, as well as a cropped in one on the bottom left there. And this is Nick Exaris's version of the Pillars of Creation, and Nick's done it in the same colour palette as Hubble as well, so he's managed to get some great detail there. I think this is with a 130mm refractor and a couple of filters that he uses to extract the different colour channels and then reblend them in the Hubble palette. And Nick's Gabriela Mistral Nebula as well to compare with Hubble. So yeah, some really nice detail, and you can see even in Nick's photo there, we can really pick out, where are we, through here, just some really nice detail in the clouds and in the nebula, although a step above there in the Hubble image. Fred Prater also compared his Gabriela Mistral to the Hubble version, and also his Helix Nebula to the Hubble version as well. So that's Fred's Helix in the main photo, and the crop out in the middle there is the Hubble version of it. Russell Smith sent in a few photos, and Russell does some great imaging as well. So that's his monochrome Pillars of Creation in M16, and that's the hydrogen alpha, which is the hydrogen emitting light coming from the nebula. And the Horsehead Nebula as well by Russell. So Russell's image is on the right, monochrome hydrogen alpha, and the one on the left is the Hubble image, which I think is, I'm not sure the colour mix on that, I think it's HSO, hydrogen red, sulfur green, oxygen blue. Bock globules is another one, is another interesting one. So the Running Chicken Nebula, which you may all be familiar with, and there's probably a photo of it up on the wall somewhere. But the Running Chicken Nebula, and a lot of objects have got what we call Bock globules, and they're these little black dark clouds that we see floating in the foreground the light emitting nebulas behind them. So block globules are cold gas and dust that's sort of cooling down, and they're usually associated with star formation. So we usually see star formation happening around these, and the James Webb Telescope, although they look black, the James Webb Telescope is able to pick out newborn stars in these nebulas as well. And these are a couple of Russell's planetary photos. So Russell's images on the left and Hubble's images on the right. Again, you can see different cloud formations over at different times. Russell's managed to get a transit of I think that's transit of Io happening across Jupiter there. Saturn, and then also Mars. Mars taken at different times. In Russell's photo, you can see the ice cap is a lot smaller, but he's managed to capture the same side as the Mars image. And the Mars image has got a much larger ice cap, so taken during the northern winter there. Steve Wilkins sent in this beautiful image as well of M16. He's got the beautiful ghostly looking photo of the pillars of creation in SHO palette. So sulfur is red, hydrogen is green, and oxygen is blue, which changes up the colour of it a little bit. And that's the full uncropped image from Steve there. Did I say Russell? It's Steve Wilkins. And that's taken with a 130mm refractor. So it's a similar sized telescope to the refractor that we have in the observatory. And this is another colorized one, different color palette of the same image as well. So well done, Steve. Got one of mine here. So this is the Horsehead Nebula in Orion. You can see that's pretty much a full frame of my field of view in my 80mm refractor, and I've cropped out the Horsehead in the right there, comparing it to the James Webb images. So James Webb is able to really pick out a lot more detail. So you can see all of this terrific detail in the dark nebula there and in the clouds coming through, comparing it to that white smudge in my photo. And then just to rub it in a little bit more, a crop out of that part gives us that view there. So it's, and then, you know, just a casual photo of a bunch of galaxies in the background as well. So really, really incredible instrument. The cat's paw. That's my capture of it on the left, and I came across this image came up on my feed and from the James Webb, so I thought I'd just compare it and see how it looked, what I was able to capture of it in my image, and I didn't realise how tight the view of it actually was. It's this section here that I'm circling there is the James Webb image. It's not actually that, it's only the small section in there. So the crop out, that's the crop of my image, and then that's the James Webb Space Telescope comparison. So you can see these sorts of features through there, mirrored here in my photo, and then you have the dark nebula, the dark clouds cutting across it there. And there's a little feature up there which I thought was a processing artifact, but there is actually a bit of a reflection nebula there which James Webb picks up. Okay, Dennis Cook managed to capture this photo on the left of the lobster, and so I've got a couple of lobsters here, and then my capture of it as well. And what we're actually comparing it to in the NASA images is, so I'll just point out here, you've got this feature in here is what we're comparing it to. So just in the heart or in the mouth of the lobster. It's called Pismus 24. It's an open cluster of some very, very large stars, very large bright stars. So that's the crop from my image there, and just I processed it separately to just see what I could get out of it. But in the Hubble image here, you're able to capture a lot more detail in the nebula, and then a closer view by Hubble picks out that star there as, in fact, a binary, two very large stars as well. And that's the full Hubble image on the right there. Greg Walton sent in quite a few shots, went through the archives and compared them to the Hubble images, and we've got C46, Hubble's variable nebula. We've got the Hubble image on the left and Greg's image on the right with an 8-inch Newtonian. And that's actually the field of view of the 8-inch Newtonian with Greg's camera. So you can see the variable, the nebula just up there, and comparing it and zooming in on it gives that comparison with the Hubble image. The Whale Galaxy, imaged by Hubble and Greg on the top, at the top there, and C53 with the Newtonian. Again, the Bok globules in Lambda Centauri, comparing Greg's image with the Hubble image. The Ghost of Jupiter at the bottom, which is a planetary nebula, which will be the fate of our star eventually. M43, De Mairen's Nebula, is that how you pronounce it? De Mairen, which is actually in Orion, and it is at the, where this is actually near, right next to M42. So when we look at M42, the Orion Nebula, it's the little circular part, and there is another photo of it right down the back there. It's a little part that is just behind the main nebula. And M51, the Whirlpool Galaxy as well, imaged by Hubble and Greg. The Black Eye Galaxy and the M65 comparisons, and you can see the common features. The black eye, you've got the dark cloud through there, and then also visible in Greg's image there, and then you've got a few details here. You've got that little dark dust cloud there, which you can make out in Greg's image, and the dark dust lanes as well. So the point is that all of these Hubble images and James Webb images, they do have recognizable features that we can image as well from the ground with fairly modest equipment too. M66 and the Sombrero. The Southern Pinwheel, which is quite a nice target to image as well. It's quite a large galaxy. It's fairly close to us and fairly easy to photograph. And that was the images, and that's our current contributors board. So we've got the 4 new contributors down the bottom, and a few of us have notched up a couple of extra points there as well. So well done to everyone. I think they were a really good collection of images for this challenge, so I think that went pretty well. Okay, so a new challenge for the next month. I'm keeping the Hubble challenge going, but from now on it must be newly acquired images. So if you're going to send in Hubble comparisons, they must be images that you've captured during the challenge period. So it's back to normal rules. We do also have, so it's a triple challenge. We've also got the lunar eclipse happening on the 8th, although it'll be a very late or a very early morning to image that one. So the eclipse begins around about 1:30. You've got the moon going into totality at around about 3:30. Is that the phrase, totality? And then it's coming out of the penumbra, and it'll continue to do so until it sets at around about 6:30 a.m. So you'll have to get up early to capture that one. Yes?
Is it 2 lunar eclipses, 8th of September and 8th of November?
I don't know.
Well, it's got to be a lunar eclipse, 8th of November. Oh, sorry.
That's my photo. Yeah, sorry, that's my photo from the last one. Yeah. And also combining this, we've got a smartphone astrophotography challenge, so you can do wide field smartphone imaging or using it to project onto through an eyepiece. Now we do have in the observatory, we've got phone holders that you can clamp onto an eyepiece and put your camera on that and use that to take a photo through a telescope. So if you want help with those, I'll be able to give you a hand at the barbecue or any other event coming up. And but you know, the smartphone photography challenge, I'm going to be a bit selective with this one. So I don't want people just snapping random photos and sending them saying, you know, hey, I got the challenge. Put a bit of effort into them, and I'll reserve the right to reject ones that are a bit, you know, weak. The goal is to get all 3, and you can use your smartphone to get a Hubble image, and that counts as 2. Or use your smartphone to capture the lunar eclipse. That also counts as 2. So if you can capture the lunar eclipse and a Hubble object using your smartphone in one photo, you're winning. Southern Hemisphere objects for the Hubble challenge you can get from the Hubble challenge website, which I'll put the link up again for you on our socials and our feeds. And then also we've got the astrophotography workshop coming in at the 13th of September. So this will be a members only workshop this year. We've got a few speakers. It'll be a $10 booking fee, which covers the talks. But generally, basically, there's pizza and a drink and coffee and tea. So the $10 just covers the cost of the food, really. And then the presenters we'll be having a few presenters, but there'll be a bit more detail on that coming up.
So sky for the month for August and September. Now this is the view of the solar system looking from above, and in that particular view, if you notice here, the sun's in the middle. All the planets are going anti-clockwise in this direction, and they're also spinning about their axes in an anti-clockwise direction as well. So you'll notice that if you happen to be standing on Earth, which you are, if you look toward, if you imagine yourself standing there on the Earth and you're looking towards the sun, you can see how, if you draw lines to the other planets, how they compare to sunrises and sunsets. So for example here, if you draw the line across to the sun, and the Earth is turning around anti-clockwise, so in other words, it's like having a line that is sweeping in an anti-clockwise direction, you're going to see Venus in the sky set, then you're going to see Mercury, then you're going to see the sun. And similarly, at the end of the day, you're going to see the sun go down, and then you'll see Mars go down afterwards on that position on the Earth. So if I just click on there, and it's advancing pretty slowly at that stage, but it'll speed up. Now the Earth was about the 4 o'clock position relative to the sun. So as you see here, the Earth would be down there, and you'll see that Saturn actually has now come back to the evening sky, and it's out there about 8:30, 9 o'clock time by the time we get towards the end of August and into September. Now you notice how here Mercury and Venus are chuffing around the sun very, very quickly, and compared to the Earth. So notice how Mercury is getting pretty close to the line of sight between Earth and the sun, so consequently you're going to lose it in the glare of the sun, and that's why you won't be able to see it in the sky at that particular time when it gets around the other side. All right, now there's the view from the Briars looking south on the 1st of September, so the moon will be fairly high in the sky around sunset. You'll notice Mars over there setting not too far behind the sun. You're getting asteroid number 2, Pallas, minor planet number 2, and Saturn and Neptune rising over in the east pretty close to each other. Now Neptune's going to be about 1 to 2 degrees away from Saturn, so if you've never seen Neptune in a telescope, you'll be able to find Saturn easily enough because you can see that by eye. And 1 to 2 degrees is like 2 moon widths away, so pretty close by for you to be able to see in a field of view. And Mars is coming pretty close to setting very early in the evening. So new moon's on the 23rd, full moon is on the 8th of September, and as Chris said, we've got a total lunar eclipse, which is at the date of the full moon by definition, and then back to the new moon on the 22nd. Now we're coming pretty close to the equinox, which is the time when day and night are of equal length. Now this is showing on the 1st of September as the evening progresses. In terms of the bright stars in the sky, you've got Antares there over in the west, and that's part of Scorpius, and you can sort of make out the tail of Scorpius there. You have the Southern Cross down here and the 2 pointers, and Achernar and Fomalhaut are fairly high in the sky. And if you want to look at each of the constellations that is visible on the 1st of September as well, that's shown there. So by the time you've got to around about the first week of September, then Saturn and Neptune are getting higher in the sky, and you get Uranus rising about 1 o'clock in the morning, and then just leading into sunrise you've got Jupiter and Venus, and Mercury will be too close to the Sun to see, and as you see, you wouldn't want to turn your telescopes around onto Mercury at that time because you could have a very nasty accident. So the total lunar eclipse, this one's taken from timeanddate.com, which shows the one that's coming up on the 8th of September. These are local circumstances, so Guido set this to be for what we see. You notice the time of night. It begins at 1:23 in the morning. So nice and early or late, depending on your point of view. Yes, Fred?
Anybody got any notions of the long-range weather forecast for that day?
I don't, no, and not at this stage. It's too far away. You'll notice these two arcs here. These are the two shadows of the moon, the penumbra and the umbra. Of the Earth, because the Sun isn't a point source, it's actually an extended source. You get two shadows, an inner dark shadow and a lighter outer shadow. And when I press play, you'll see the moon start to dive into initially the outer shadow, which is called the penumbra, and that will be only a fairly slight, there we go, so it reaches into the penumbra. You'll see maybe a slight dimming of the moon, and then when it touches the umbra, that's going into the darker inner shadow of the Earth, and then it goes right into the shadow, and when it's fully within the shadow, then you're inside the eclipse. It may not be the darkest point, but you're at the point when you're fully inside. So you notice the orientation of it. So maximum eclipse there occurs at 4:12 a.m. in the morning. So this is something that's going on for a period of hours. It's not a super deep eclipse, so it's probably not going to go a brick red or a grey colour, but it should, I would think, normally go an orange or an orangey red, particularly only going that far in. And now it's actually leaving the umbra at the other side. So again, until it actually sets. So you won't actually see the end of it from here in Victoria because it will go below the horizon. Now the apparent sizes of the planets, if you're looking at them through telescopes, obviously Jupiter is the dominant one if you're willing to get up in the morning at the moment. Saturn, you can see the rings of Saturn are pretty close to edge on still, but they will slowly open up as the months ahead go by, and it's always an impressive sight to see. And if you do have a go at Uranus and Neptune, notice the size of them relative to even Saturn. So don't expect a very big disk to be looked at. Now, comets in the sky, you'll have better luck searching for the Loch Ness Monster, I think, because there's no comets in the sky brighter than magnitude 10. And similarly, meteors, go looking for Nessie instead. And as usual, the sky for the month, the sources are Stellarium, NASA Eyes on the solar system, Astronomy 2025, which is the final quasar almanac from Wallace Dawes and Northville, and timeanddate.com. So tonight's feature, this is about from Apollo to Artemis, since we've lost Jim Lovell recently. And this is two talks, one given by Dr. Harrison Schmitt, who visited Mornington here about 20 years ago. We couldn't quite get him here on site that evening, but the Society had a table at a dinner in his honour at the racecourse in Mornington, so we all got to meet him. He's the only geologist and only scientist to walk on the moon on Apollo 17, and that's a picture of him next to the famous Big Rock, which was named after his daughter. After this particular talk, it's from 1973, so you'll notice the quality of the video is not quite what we're used to these days, because it's a completely different technology. Then we'll listen to Dr. Giulia Magnarini from the Natural History Museum, and she's also on NASA's sample analysis program for Apollo 17. So when Apollo 17 came back, a lot of the rocks were sealed, and they've never been opened since coming back from the moon. And that they're at the process now of opening them up to be reanalyzed using current techniques. And that was always the plan. So in other words, they would be pristine samples once technology has had a chance to move on sufficiently. So she's involved in that particular project. So this she'll give what was a public lecture from a couple of months ago at the Geological Society in London.
My name is Simon Thompson. I'm the Chief Executive here at the Geological Society, and we're very excited to have Dr. Giulia Magnarini here, who I'll speak about a little bit more in a few moments. So I'm not a geologist, but I did used to be a little boy, so the idea of watching an astronaut talk about the moon is exciting to me too, although I gather it is very geological. So to begin with, we'll be watching a recording of a lecture given by Dr. Harrison Schmitt. I gather he knows he's still with us. He was born in 1935, and I gather that he knows that this event is going on. So that's quite exciting in itself. In December 1972, Dr. Schmitt walked on the moon, and in 1973, we're honoured to receive him at the Geological Society for the talk you're going to see. So the recording is of the Geological Society's 28th William Smith lecture, entitled Apollo and the Geology of the Moon, presented by Apollo 17 astronaut Dr. Schmitt in 1973. And Schmitt remains the only geologist and, in fact, the only professional scientist to ever have walked on the moon. And it was his mission that was the final mission so far to the moon, I gather. After the recording, Dr. Giulia Magnarini, will give a talk titled From Apollo to Artemis, Paving the Way to the Next Giant Leap in Lunar Exploration. Giulia is a researcher at the Natural History Museum, working on surface processes of bodies in the solar system, and Giulia is involved with the NASA Apollo Next Generation Sample Analysis Program, studying newly opened Apollo 17 samples.
It is my privilege to continue your society's honoring of William Smith, certainly one of the, if not the most outstanding geologist in our history. We did not do very much more than to build on the traditions and in geology that he established and the principles by which we have all, in our various ways and countries, learned to study that particular science. As a matter of fact, prior to the mission and the process of naming or designating craters in the valley of Taurus Littrow, where we conducted our explorations, I picked Smith as one of the people that I personally wish to honor. And there is a crater on the northeast corner of our exploration area that is, in fact, named Smith in his honor. It also was the closest I could get to naming a crater after myself. I may talk too much today. I very often do. But I would like to, on this my first and visit to London and to the Society, give you as broad a view of what Apollo science is, of what this valley of Taurus Littrow and the Earth looked like to me as I was in space, and finally what possibly Apollo may mean in the general history of mankind. Now, this all may take longer than I anticipate, and I would also like to have an opportunity to break a little bit with your tradition and answer questions if the time allows. Could I have the lights down, and I'll start. Apollo required a Newtonian match, if you will, between the explorer's sunrise and the moon's sunset, shown here. Sunset on the far side of the moon was not always so starkly tranquil as it is now. About 4.6 billion years ago, when the moon was approximately its present size, the sun probably set on a glowing, splashing sea of molten rock. Storms of debris still swept this sea, mixing, quenching, in fact, outgassing and remelting a primitive melted shell. This shell had been created by the great thermal energy released in the last violent stages of planetary accretion. Inside the melted shell, the crust of the moon was gradually taking form through processes of fractional crystallization on a planetary scale. This initial differentiation of the moon produced a combined crust and upper mantle a few hundred kilometers thick. The crust rich in calcium and aluminum, and the upper mantle rich in magnesium and iron. At the base of this melted shell, an immiscible dense liquid of iron and sulfur probably accumulated. Most of the major chemical differentiation we have observed in the moon may have been established with the fractionation of siderophile and chalcophile elements into this immiscible liquid, combined with the fractionation of major and minor elements extracted by the fractional crystallization of silicate minerals in the melted shell as a whole. In these interpretations, the moon may be a pitted and dusty window into our own planet's past. About 4.4 billion years ago, the surface of the moon's outer crust must have looked not unlike the highland areas we see today, such as these on the far side of the moon. As the debris storms continued their declining ways, this cratered and pulverized outer crust was saturated by craters more than 50 kilometers in diameter. It is now composed largely of pulverized plagioclase feldspar, a silicate mineral, as you know, rich in calcium and aluminum, mixed with possibly 30% of mafic minerals. Now, between 60 and about 200 kilometers beneath this outer crust, our seismic evidence indicates that the upper lunar mantle is probably composed largely of pyroxene and olivine, silicate minerals rich in magnesium and iron. Both the mantle and the crust, however, have been greatly modified by later events and materials. It may be of interest to note at this point that the oldest rock complexes on Earth, that in these oldest rock complexes there are rocks called anorthosites, which are rich in calcium and aluminum, and as are the very old crustal rocks on the moon. The early differentiation of plagioclase-rich crust on Earth may account for at least the initial concentration of elements comprising these previously and still mysterious rocks. Understanding their origin and evolution is not a trivial problem, as most of you are aware, as most of our titanium resources are presently found in such rocks. As the residue of creation was consumed by Earth and Moon alike, the debris storms decreased in frequency, although not without occasional unusually massive reminders of the past. Sometime prior to about 4.1 or 4.2 billion years ago, large basins such as Ingeny here began to form by major impact events at a time when they could not be obliterated by smaller collisions. The older of such basins, such as Tranquillitatis, are irregular in shape, have shallow original floors, and contain no large concentrations of mass. The younger basins, such as Serenitatis, are circular in shape, have deep original floors, and contain large concentrations of mass called mascons, typically of NASA. Although all of the great basins, we can blame JPL for that as a matter. Although all of the great basins appear to have been formed by major impact events, these differences indicate a major change in the mechanical properties of the crust about 4.0 billion years ago. The final crystallization of the residual liquids of the melted shell may have occurred at this time in order to strengthen the crust. Now, there are many good reasons to believe that the Earth's crust suffered the same violent indignities as did the Moon's. Although the subsequent 4 billion years of Earth history have masked the effects of this violence, there are now many new things to look for and many new lines of interpretation to pursue. For example, Throughout the Earth's crust, there have long been recognized regional provinces that are rich in certain elements and are the locus of ore deposits of those elements. Loci of ore deposits of those elements. My home country in the southwestern United States is one such geochemical province rich in copper. Our present understanding of the origin and structure of these provinces is very weak, even though much time, effort, and money has been spent in endeavoring to understand. Locked in the mechanics of the formation of the very large lunar basins and their penetration into the crust and in the distribution of ejecta around such basins may be the answers to geochemical provinces. Near the conclusion of the period of large basin formation, about 3.9 billion years ago, the moon's interior, through the accumulation of the heat of radioisotopic decay, gradually reached temperatures by which it could begin to influence the character of the surface regions. First, a core of a liquid solution of sulfur and iron may have accumulated. This may have occurred in part by the gradual gravitational migration towards the moon's center of the immiscible liquid from the melted shell period I mentioned previously. In this core, a remarkable and still little understood phenomenon apparently occurred. An electric dynamo probably came into existence, began to perpetuate itself, and produced a magnetic dipole field about 1/25 of that presently associated with the Earth. Although the dipole field has disappeared, the magnetic anomalies left in crustal rocks persist to the present. The largest of these anomalies is, appropriately, near the crater Van de Graaff, shown in this slide. The second event generated by the moon's interior processes was the apparent eruption on the surface of light-colored plains-forming materials. Visual and geochemical studies conducted from lunar orbit indicate that these light-colored materials are composed largely of the pulverized remnants of the ancient crust. Such feldspar-rich materials appear to be eruptive and to have partially filled all of the great basins that then existed, such as the basin Gagarin, shown in this slide. Their eruption may have been driven by the first melting and upward migration of the materials, rich in radioactive and gaseous components, that would later concentrate in much larger volumes and much purer form to form the Maria. Just after the last of the large basins were created, about 3.9 billion years ago, the final major internally generated episode of evolution on the moon took place. This chapter of lunar history tells of the flooding of all the great basins on the front side of the moon by vast, now frozen oceans of dark basalt. Only the very deepest of basins on the far side were affected by the formation of the Maria, such as the basin Tsiolkovsky is shown here. To some degree, however, all portions of the outer crust of the moon must have been permeated up to a general Mare sea level, if you will. This tremendous upwelling and extrusion of molten rock was probably perpetuated by heat from radioisotopic decay, and in this case, portions of the moon's upper mantle or even deeper intermantle probably melted. The extrusion of Mare basalt may have been very rapid through the intensely and deeply broken outer crust. If this was true, then each basalt-filled basin, such as Tsiolkovsky, may be a single cooling unit and similar in internal structure to our own planet's basaltic and ultramafic stratiform sheets. Variations in the internal composition of the moon or in the depth of melting caused the period of Mare flooding to span the time from 3.8 to about 3.0 billion years ago, one of the younger Mare basins being Tsiolkovsky, again shown in this slide. Such variations in composition or depth of origin also caused profound chemical differences in the basalts that were produced as this time passed. Near the end of several of the periods of Mare flooding, mantles of dark, chemically distinct basaltic pyroclastic debris were deposited over large areas. Then a relative quiet settled forever on the surface of the moon. When the waves and currents on the Maria had finally been arrested, the moon's appearance differed only slightly from that of today. We should now note, I believe, that the oldest rock terrains on Earth also contain vast layered rock sheets, which in aggregate are basaltic or ultramafic in composition. Their resemblance to the lunar Maria may be more than coincidental. Again, as with the anorthosites, this is not a trivial problem because much of the nickel, chromium, and platinum group metal resources of our planet are located within these sheets of rock. Now, about 3 billion years ago, except for faint rumblings and occasional sharp ringings as seismic reminders of the past, the storied moon apparently completed the record of its tail, at least the record exposed to us in the lunar crust. There are some indications, however, of a brief period of later internal activity, possibly a convective overturn of the lunar mantle, but nothing like the continuing activity of Earth and Mars. The sequentially young ridge and volcanic system in Mare Procellarum, the great regional graben systems across the southeast quadrant of the moon, and the light swirls of apparent alteration scattered around the whole moon may reflect the embryonic stresses of aborted evolution. Now, what was the history of events in Apollo that have led us to this first-order interpretation, and that's what it is, a first-order interpretation of the evolution of another planet? Much of what I say is still speculative. However, many of the lunar scientists presently working in the field will generally agree that the framework I have just established is one which they are using as their working hypothesis. The far horizon of Mare Tranquillitatis, shown in this picture, holds a unique place in the annals of science. The events which history will remember as having changed forever the course of that same history was the landing of Apollo 11 by Armstrong, Aldrin, and Collins. Science, for its part, had finally had real and factual insight into the temporal dimensions, if not all of the actualities, of the evolution of our sister planet. The ages of at least major portions of the rocks from the lunar crust were found to be very old relative to terrestrial rocks and to previous estimates of the ages of lunar rocks. In fact, the fact that the relatively young appearing Mare of Tranquillitatis was 3.7 billion years old seemed to confirm that we would be studying our own past along with that of the moon. The rocks of the Mare were basaltic as predicted. However, they were not only unusually rich in iron and titanium and poor in sodium, but were highly differentiated chemically relative to solar and meteoritic elemental abundances. The basalts also appeared to be locally differentiated through fractional crystallization. Through fractional crystallization. The debris sampled in the landing site that was present in the soils seemed to confirm the Surveyor 7 results from some years previously, that the lunar highlands were rich in calcium and aluminum. Possibly most important to science, Apollo 11 confirmed that much of our intellectual experience in geoscience was applicable to our studies of the moon. Conrad, Bean, and Gordon on Apollo 12 landed within a few hundred meters of a previously landed Surveyor 3 automated spacecraft in Mare Cognitum, southwest of the part of Mare Imbrium that I'm showing here. Their mission returned obvious complexity to lunar science after the emotional early simplifications following the results from Apollo 11. The structure of the gardened upper few meters of the lunar surface became a complex history book, not only recording solar and cosmic events, but showing that the relative mobility of volatile elements in high vacuum, such as we had at the lunar surface, would be of great significance in interpreting geochemical measurements. Representatives were uncovered of heretofore unsuspected rocks rich in potassium, rare earth elements, and phosphorus, apparently recording a fractionation event that occurred about 4.5 billion years ago. The range of ages of the Mare basalts was extended downward to about 3.2 billion years from the 3.7 we saw on Apollo 11. And it was found that their major chemical variability extended to relatively low titanium varieties. The surface units of the Mare were also confirmed to be differentiated flows on the order of 40 meters thick. To the east of the Mare Cognitum landing site of Apollo 12 and south of the crater Copernicus shown here, we planned the landing of the Apollo 13 mission. We were anticipating insight into the intensity and timing of the event that formed the Imbrium Basin through the study of its ejecta blanket. Instead, as you may recall, we received new insight into ourselves. The courage of Lovell, Hayes, and Swigert, and the resourcefulness of the controllers of their mission following the explosive destruction of the service module gave one of history's most graphic examples of man's potential in the face of extreme adversity. However, Apollo 14 and Shepard, Mitchell, and Russa inherited Apollo 13's exploration plan at the crater, or near the crater, Fra Mauro. The mission told us that not only did the Imbrian event occur barely 100 million years before the oldest Mare basalt extrusions, but that such massive collisions cause much more geologic disruption and transfer much more heat energy into a planet's surface than we had ever before imagined. In fact, it now appeared that much of the pulverized crustal material ejected from the large basins moved many hundreds of kilometers across the moon's surface and had many of the characteristics of ash flows. The Apollo 14 mission also confirmed the extreme chemical differences between the highlands and the Mare as detected on previous missions. The Apollo 15 mission to Hadley Rill at the foot of the Lunar Apennine Mountains, there's the Hadley Rill, introduced a new scale to lunar exploration. First, Scott, Irwin, and Worden began to look at the whole planet through the eyes of cameras and electronics, as well as the eyes of man. Then, on the moon's surface, they reached beyond our earlier hopes and began to rove and observe the wide variety of features available for investigation. The varied samples and observations from the vicinity of Hadley Rill and the mountain ring of Imbrium propelled our knowledge of lunar time and processes back past the 400 billion year barrier we had seemed to see on previous missions. We began to vaguely see into the first half-billion years of lunar evolution and into the details of the melted shell period. In addition, we expanded our delineation of the complex volcanic processes that created the present Mare surfaces. These processes were now seen to include not only complex lava flows, but possibly processes of volcanic erosion that could create the Mare rills. We also discovered once again how pervasive are the effects of contamination of these surfaces by impact processes. With Apollo 15, we also finally established a geophysical net, particularly a seismic net, by which we could begin to see the inside of this planet. The structure of the planet, as described earlier, had begun to be deciphered. Also, we began to be able to correlate our landing areas around the whole moon by virtue of geochemical X-ray and gamma ray mapping from orbit. These remote sensing investigations disclosed the provincial nature of the lunar chemistry, particularly highlighting differences in aluminum silica and magnesium silica ratios within the Mare and the highlands, and by outlining anomalies in the distribution of uranium, thorium, and potassium, the gamma ray information suggests that large basin-forming events are capable of creating surface geochemical provinces through the ejection of deep-seated material. Possibly of equal importance with all these discoveries was the realization by ourselves, and on this mission by millions of people around the world, that there yet existed sheer beauty and majesty in views of nature previously outside human experience. I think one of the great driving forces of all geological explorers in history. Here we see the sunrise shadows of the Apennines as they retreat across the eastern plains of Imbrium. To the southeast of this majestic point on the moon, Apollo 16 landed and found that we were not yet ready to understand the earliest chapters of lunar history exposed in the southern highlands. In the samples returned by Young, Duke, and Mattingly from the Descartes area, we seem to see that the major central events of lunar history were compressed in time far more than we had been prepared to guess. There are indications that the formation of the youngest major lunar basins, the eruption of light-colored plains materials, and the earliest extrusions of Mare basalts took place over about 100 million years of time, about 3.9 billion years ago. Also, indications are present at Descartes that the light-colored plains may be the loci of many of the observed regional magnetic anomalies, suggesting that they formed, that is, the plains formed, as single cooling units that were initially above their Curie point. Near the coast of the great frozen sea of Serenitatis, shown here on the horizon, Apollo 17 carried Cernan, Evans, and myself to visit the valley of Taurus Littrow, a dark bay-like indentation into the rim of that sea. The unique visual character and beauty of this valley was, I hope, seen by most of you last December. The unique scientific character of this valley helps to mitigate the sadness that with our visit the Apollo explorations ended. If this end had to be, it would have been hard to find a better locality to synthesize and expand our ideas on the evolution of the moon. At Taurus Littrow, we looked at and sampled around the lunar module that you see in the center of this picture the ancient lunar record ranging back from the extrusion of Mare basalts about 3.8 billion years ago through the formation of the Serenitatis mountain ring and thence back into materials that may reflect the very origins of the lunar crust itself. Also, we have found in our study materials and processes that range forward from the formation of the earliest Mare basalt surfaces through 3.8 billion years of modification of that surface. This modification includes the addition of mantles of chemically distinctive orange and black glasses, which may be the culmination of processes once active within the deep interior of the moon. These glasses surprise us once again. Their 100 million year exposure age is young, as expected, but their 3.5 to 3.7 billion year cooling age was not as expected. The explanation for this difference is not yet completely obvious. For all of our Apollo missions, we left the moon before the lunar sunrise, shown here, had progressed into the vast regions of the lunar west. There is Mare Procellarum, where the young mysterious features of that region's central ridge system still awaits the crew of a mission diverted after Apollo 13. There is Mare Orientale, whose stark alpine rings have been viewed closely by man only in the subdued blue light that comes from Earth. The promise of the story in these regions is not diminished, but seemingly watches for the progression of the sunrises and the landing craft of another generation of explorers. When that time comes, we may merge the scientific revolution brought about by Apollo on the moon with the simultaneous revolution brought about by new insight into the origin of ocean basins and continents on Earth. We may begin to understand the great stresses and strains within our own crust as ocean floors grow and continents move. These stresses and strains, as you know, profoundly affect the everyday lives of people living within belts of present earthquakes and volcanic activity, and have affected the distribution and control of ore deposits upon which our civilization is based. Within future understanding of the frozen ocean of basalt of Mare Procellarum and the vast ridge system and volcanic system that splits it, may lie further inspiration for all of us. In this, our new knowledge from the moon will never become a resource until it is married to imagination. It is thus and only thus that the scientific legacy of Apollo will be realized. The personal legacy of Apollo is what I would like to treat in my next few moments. I would like to tell you next about a specific place I have seen in the solar system. This place is a valley on the moon now known as the Valley of Taurus Littrow. Taurus Littrow is not a name chosen with poetry in mind, but as with many names, the mind's poetry is created by events. Events surrounding not only 3 days and the lives of 3 men, but also the close of an unparalleled era in human history. The valley, however, has been unchanged by being a name on a distant planet, while change has governed the men who named it. The valley has been less altered by being explored than have been the explorers. The valley has been less affected by all we have done than have been the millions who, for a moment, were aware of its towering walls, its visitors, and then its silence. The Valley of Taurus Littrow is confined by one of the most majestic panoramas within the view and experience of mankind. The roll of dark hills across the valley floor blends with bright slopes that sweep evenly upwards, tracked like snow, to the rocky tops of the massifs 2,300 meters above. The valley does not have the jagged, youthful majesty of the Himalayas, or of the Rockies, or of the glacially symmetrical fjords of the North Countries, or even of the now intriguing rifts of Mars. Rather, it has the subdued and ancient majesty of a valley whose origins appear as one with the sun. The massif walls of the valley rise to heights that compete well among other valleys of the planets, but they rise and stand with a calmness and unconcern that belies dimensions and speaks silently of continuity in the scheme of evolution. Still, the valley is not truly silent. Its cliffs yet roll massive pages of history down dusty slopes. Its bosom yet warms the valley floor and spreads new chapters of creation in glass and crystal. Its craters yet act as the archives of their sun. The valley has watched the unfolding of thousands of millions of years of time. Now it has dimly and impermanently noted man's homage and footprints. Man's return is not the concern of the valley, only the concern of man. The Apollo explorations we have watched and lived were man's first halting but clearly personal look at his universe. Our unique character among the living species of nature is carried forward in many ways. One outward reflection of this character is that we have had the audacity to try to understand our place in this universe and in its future. We've had the further audacity to try to use that understanding to alter the universe and to more fully understand the Earth, using in large measure the corrected vision from space. Like our childhood's home, we really see the Earth only as we leave it. First, there are the basically familiar, though expanded views of Earth from the now well-traveled orbits. Banded sunrises and sunsets, changing in a few seconds from black to purple to red to yellow to searing daylight, and then back in never-ending progression. Tinted oceans and continents with structural patterns wrought by aging over 4.5 billion years of time. Shadowed clouds and snows ever varying in their mysteries and in their beauty. And the warm fields of lights by night and of homes by day, created by men but seen without the boundaries of their minds. But then as we leave what is familiar, the strange new perspective is that of the Earth filling only one window, and gradually not even doing that. The disquieting thought is that it is no longer the Earth of our past. It is only a fragile blue globe in space. There's no apparent purpose in the cyclic wandering of our ship the Earth through its own universal sea. The forces that hold us to this invisible course have been long explained, but never truly understood. There are waves that we do not feel, there are storms we cannot see, and there's history we have not read. Only the hope of continuity has always been reality during our voyage around the sun and through the galaxy. Again, like childhood's home, which we now only visit, changing in time but unchanged in the mind, we see the full Earth revolve beneath us. All the tracks of man's earlier greatness and folly are displayed in our window in the course of a single day. The Roman world, the explorers' paths around the continents, the trails across old frontiers, and the migrations of peoples are accented in their significance by our own act of seeing. Then, with some of the disappointment felt as loved ones age, we see the gradual change with each revolution, as a full Earth changes to half, then to crescent, and then to a faint moonlit hole in space. The line of night crosses water, land, and cloud, sending its armies of shadows ahead. In its inevitable rhythm of motion, we see that night, like time itself, masks but does not destroy beauty. At last, when we are held to our own cyclic wandering around the moon, we see the Earth rise, that first and lasting symbol of a generation's spirit, its daring, and its imagination. Having seen the Earth rise as did our predecessors, we have reaffirmed man's evolution into his universe, never to be satisfied with only the beauties and comforts of that rising Earth. Paradoxically, we also find enhanced awareness and appreciation of that which we are now so willing to leave behind. You may feel that this new view of the Earth must have more and deeper spiritual meaning than I have given you. It must prove that there is a God, or it must prove that there is no God, or it must prove that it makes no difference. We will not make the choice for you. We only make it for ourselves. Even then, it turns out to be a choice we have made already in some other unaware time. All that is absolute and all that will stand forever is that man was there to see for himself. Thank you very much, ladies and gentlemen, and I'd be happy to answer any questions.
I have to say, I feel a little bit intimidated. The idea of giving a talk straight after such a detailed geological report by Harrison Schmitt. But it's also quite exciting. It's really exciting to be here and to share and being able to share the interest and passion for the Apollo program and the lunar exploration. So if there was just one single thing that I would like you to remember from tonight, going back home and think, what did I learn from tonight? So the only one thing would be that the legacy of the Apollo program, despite more than 50 years have elapsed since the last Apollo mission to the moon. So the Apollo legacy still continue nowadays and is actually serving to prepare for the NASA Artemis program, which will soon bring humans back to the moon, including the first woman and the first person of color. And so really exciting time ahead for lunar exploration, but in more general for space exploration. I would like you to stop for one moment and think, when was the first time that you heard of Apollo? Or maybe the first time that you learned about Apollo? If, I don't know, maybe Apollo has affected your life somehow. And perhaps for some of you, this is the first time. So in that case, it would be quite cool for me to have this responsibility to get you into the Apollo fascination. So in my case, in my personal case, I have no recollection whatsoever how the fascination for Apollo came. But what I know is that around the mid-90s, 12, maybe 14 years old Giulia, okay, maybe we will go at some point, did this, okay? She took a stick and she carved it and decorated, thinking of Apollo 11 and pretending it was the majestic Saturn V. But this is the image that really left a mark in me. And yeah, this is a photo mosaic we saw from Harrison Schmitt, this image. And the astronaut in this photo mosaic, he's Harrison Schmitt. And I was a first-year geology student back then, and I saw this photo on my geology textbook, and the caption was saying something like, something, Harrison Schmitt, the only geologist to work on the moon. I thought, what? I want to become a planetary geologist. But probably only a few hours later, I had already forgotten about my pledge, and so life took me out of places, until one day, more than 10 years later, some sort of life crossroad, I remember this image, and I decided to enroll to a degree in planetary science. And little I knew that a couple of years later, I would attend a lecture about the geology of the Apollo 17 landing site by Harrison Schmitt, and even less I knew that a few months later, he would become one of my PhD advisors. So my PhD project on big landslide in the solar system came to exist because of an enigmatic landslide at the Apollo 17 landing site that Harrison Schmitt visited. And so to some degree, I'm here and I do what I do because of Apollo 17. So this is my personal Apollo anecdote, and I would really love to hear if you have your own Apollo anecdote later at the drink reception. But we should just continue talking about the Apollo now, and how the science of Apollo shaped our understanding of the moon. So the activity on the ground of the Apollo mission included involved a combination of sample collection and geophysical experiments. I'm going to talk about the sample and the rocks that were brought back to Earth in a bit, but I just would like to start with mentioning two geophysical experiments that were conducted on the moon that really, gave us important information about the moon. The first one is the lunar seismic experiment. So the Apollo missions, the Apollo astronaut left deployed on the lunar ground seismometer, and the seismometer were left active until 1977. So about 8 years of recording of lunar seismic shaking. And so from those recordings, we came to know that on the moon there are moonquakes. There are two different types of moonquakes, shallow moonquakes, that occur in the shallow crust, probably down to a maybe 10 kilometers depth. And then we have deep moonquakes that occur more or less between 700 and 1,000 kilometers at depth. We still don't know the exact origin for these moonquakes, but that's what we found out with the lunar seismic experiment. The other experiment is the lunar laser ranging experiment. So the Apollo astronaut deployed this laser reflector, and if it works, someone else will.
In 1969, the
there's no
astronauts
sound.
on Apollo
Anyway,
11 positioned reflectors on the surface of the moon, and we're going to shoot a laser off one of them and let the light bounce back into this photomultiplier.
Laser.
There it is. There's the spike. 2.5 seconds for the light to return. That's the moon. We hit the moon.
Here we go. So with this experiment, they hit the moon, but what you can do with that time of the travel time of the laser, you can extract the distance of the moon. So with that experiment, we know how far we are from the moon, and what we found out with continuous measurement, that the moon is actually moving away from us few millimeters every year. But it's really from the Apollo samples that we anchor the lunar science. So the lunar samples have been really fundamental for example, calibrating remote sensing data. So we have a rock and said, okay, this is what we are observing with our observation from orbit. So we can calibrate those information. We can also calibrate our method for attributing absolute ages to planetary surfaces. We obtained some information about porosity and density that are also useful for other satellite data like gravitometer. And we could learn a lot about the petrology and geochemistry, and so learning about the lunar evolution of the crust and the interior. We learn a bit about the magnetism and possible existence of a lunar dynamo in the past, but we can also learn about the source area for meteorite. We have lunar meteorite, but also learning about the cosmic environment. So everything that comes from space, from cosmic rays to solar wind. Okay, so Apollo is not the only mission, the only programs that brought lunar rocks back to Earth. We also have 3 Soviet missions, the lunar missions, and more recently we also have 2 Chinese missions, Chang'e and the Chang'e 6, the latest one, 2024, the only one to sample the far side of the moon. But Apollo is the program that brought back 382 kilograms. If you want to think about, let's say, 4 baby elephants, okay, or rocks. And from these lunar rocks, we learn a lot. As we heard from Harrison Schmitt earlier, we learned a lot about the geochemistry, the petrography, and so tied in all this information together, the lunar sample have been really important to, for example, better defined our understanding of the lunar origin. So the Apollo samples were the most important piece of information in support of our current preferred, let's say, favorite theory for the formation of the moon, which is called the giant impact hypothesis. So in this hypothesis, we have a Mars-sized body called Theia, and at some point very early in the history of the solar system, collided with the Earth and created chaos, debris all over, orbiting the Earth, and from this debris, the moon formed. But Apollo sample also helped us to understand the lunar crust formation, and the name of the hypothesis is called the magma ocean hypothesis. That suggests that, again, very early in the history of the lunar formation, the outer moon, let's say, was entirely molten. So there was this magma ocean. So with the following cooling of this magma ocean, there was crystallization of mineral. They follow really strict rules, what crystallized first. So we have the heaviest mineral, olivine and pyroxene. So we have magnesium and calcium type of mineral that will sink into this ocean. And then what is left, we will start crystallizing some sodium-rich minerals, forming the plagioclase bearing rocks. And here we have just few examples of a basalt that is supposed to be the rock in the lunar mantle, and then the anorthosite that form the lunar crust. So the anorthosite are quite this whitish type of rock, and those are the bright region that we see on the moon, and the basaltic rock are much darker, and for those darker region that we observe on the lunar near side. So this is very simplified version of this hypothesis. There's a lot of complexity with the exchange between the crystal and still some of the magma left over, and all this complexity are represented from the Apollo sample. And but spoiler, we need to go to other places, okay? So because then there could be much more that we can learn with just a sample few location on the moon. And just to say, this hypothesis, the magma ocean hypothesis, has now been transferred to all the other planets in the inner solar system, and that's what we think how primary crust form for all the other forming planets. And so this is underlying the importance of studying processes on the moon, because the moon still have retained a record of ancient processes that unfortunately are not available anymore on active, geologically active planets like Earth or Mars. And so similarly, the moon is a great place where to study lunar impact processes. So this is a new impact, I think is about 18 meters in size, that thanks to temporal images, NASA people found out in 2013. And the majority of the Apollo samples are actually rocks that have been formed/modified by impact cratering. So the lunar surface retain the record of impact cratering since the very beginning of its geological history. And on Earth, we don't have, let's say, this, I don't want to say privilege, we're really lucky that we have an atmosphere that is protecting us from space rocks. But this in turn doesn't allow us to really understand this fundamental process across the solar system. And it's not just about the science of understanding this process, but if we are planning on going back to the moon and staying there for long and maybe permanently, we really need to understand this process, the flux, and the danger that could come with that. And again, these are just really nice 3D model made by NASA of some of the breccia samples, which are these rocks created by impact cratering. And so talking about impact cratering, or impact in general, so the lunar surface has been like constantly bombarded for 4.65 billion years by meteorite, macrometeorite, gigantic space rocks forming the large impact basins. And so all this process have formed the lunar regolith, which is the lunar soil. So it's this incredibly fine layer that could arrive up to a couple of meters that completely cover the lunar surface. And that's the Neil Armstrong footprint. And you can see how really fine grain, and that dust was all over the astronaut spacesuit. It was really, really annoying for them to work around that, and even going back to the spacecraft. So the Apollo has provided with really crucial information, again, for also what is coming next. Going back to the moon, how to deal with lunar regolith, and also not just for the instrument safety, but also for astronaut safety. This is a really fine particle, so it's really important that the astronaut will be safe from annihilating these fine particles. And but apart from that, the lunar regolith, as I mentioned, it records it. It can be considered a sort of an archive of anything that of the lunar environment, of the cosmic environment on the moon. So recording all these events from impact cratering, but also implantation of solar wind or cosmic rays. So it's really important to understand all these processes. And it's not just, again, for the science, but also for us. Again, we are lucky, we are protected by an atmosphere, but we really need to understand these processes, especially if we want to move to other planets with not an atmosphere that is not as thick as ours. And here is an image of a pit, probably a collapsed lava tube, showing some layering. And this is a layering of lava flow. And in between, we may expect some lunar soil, lunar regolith have formed in between this volcanic or lava flow event. And so we can imagine going back, maybe being able to sample and reconstruct the sort of stratigraphy of this regolith, and then really being able to obtain information about the lunar cosmic environment. And so being able to access this record that, again, on our planet is not available. And this is the final mention I wanna make about the importance of lunar samples. And we saw this sample place in the Harrison Schmitt presentation, and it's about volcanic glass beads. And there should be a sound. This is a famous finding of orange soil. So this is a 2 minutes.
Oh, hey! Wait a minute. What? Where are the reflections? I've been fooled once. There is orange soil. Well, don't move it till I see it. It's all over. Orange. Don't move it till I see it. I've stirred it up with my feet. Hey, it is! I can see it from here. It's orange. Wait a minute, let me put my visor up. It's still orange. Sure it is. Crazy. Orange. I've got to dig a trench, Houston. Copy that.
And we just go to the trenches.
It really is. Same color as these. Temperature on the SEP is about 100 and... Temperature on the SEP's about 102. It's almost the same color as the LMP decal on my camera.
Okay, now we also have Astro.
Okay, copy that.
It's just a
That
big
is
word.
orange, Jack. Fantastic, sports fans. It's trench time.
Yes.
You can see this in your color television, I'll bet you. How can there be orange soil on the moon? Jack, that is really orange. It's been oxidized. Go around and get the lunar sounder over here. It looks just like an oxidized desert soil. That's exactly right.
Okay, so, well, that was orange soil and unexpected. You know, usually everything on the moon is quite grayish. And it turned out that the soil sample contained this volcanic glass bead, and the orange comes from these beads being rich in titanium. Okay, but in the field, he mentioned, oh, this is probably oxidized soil from like desert type of material. But at the analysis, when they discovered these are glass beads, so these beads form through processes like a fire fountain, okay? And so to have this type of processes, you need gases, volatiles. And this was something, well, in a way unexpected for the back then type of idea we had of the moon, of a place completely dry. So if you don't have, you are not going to have, apart from water, but any type of volatile. So that implied that some gas was present in the mantle, or anyway, being able to generate this type of volcanic processes. But then maybe it's now 15 years, like also many decades after the Apollo, these samples were reanalyzed with more advanced analytical capability. And from those analyses, researchers found that these glass beads contain a lot of water. But again, I'm not talking about liquid water, but molecular water in the form of hydroxide molecules, so the OH molecule. And that was something quite surprising. So again, with our notion of the moon being a dry place, maybe we need to rethink what is actually the water content in the moon. And I mentioned, I just mentioned how revisiting, reanalyzing Apollo sample many decades later with more advanced technologies or instruments are available that can really change our view of some of our previous understanding of the moon. And so in this regard, I really would like to talk to you about two core samples that were collected at the Apollo 17 landing site, and NASA decided to keep closed, waiting for when more advanced technology would be available in the future. And this is within the NASA ANSA, that stands for Apollo Next Generation Sample Analysis Initiative. And okay, so from Harrison Schmitt presentation, we just saw an image. I have a video of the Taurus Littrow Valley, but it was taken from the command module of the Apollo 17. And probably distract you, there was the shadow of the lunar module just ahead. And that's the valley located between those two big impact basins. There was a beep. So this is the lunar lander, and talking about legacy, I don't remember when it was launched, but anyway, there's an incredible orbiter. I think maybe it was 2007. The Lunar Reconnaissance Orbiter has been providing incredible high-resolution images of the lunar surface, and so this is the image from LRO of the Apollo lander at the Apollo 17 landing site. And you can see how instead on the very right of the image, there's another thing, and that's the lunar rover. And you can also really appreciate the tracks left by the rover. So this is a testimony that we've been there also. So we have a legacy. And again, we saw this image from Harrison Schmitt presentation. That mountain over there is called the South Massif. And that's from where the enigmatic landslide mentioned at the beginning came from. The landslide is called the Light Mantle. This is just to show you the route of the that the Apollo 17 astronaut made over 3 days field work. And so this is the shape of the landslide. It's called the light mantle because it has a higher albedo compared to the surrounding material. It's long 5 kilometers, and so that was quite enigmatic for that. So the initial idea on how this formed suggested that in the bottom left of the image instead, you see a quite large crater from which rays depart. And so the idea is that some of this material that were ejected from this impact travel across the lunar ground and hit the back of the mountain, triggering the landslide. Sounds crazy, but it can be possible, okay? But there's another competing idea about how this landslide form, and it's about moonquakes. So in the valley, we have ancient fault from the expansion following the formation of the large impact basin, but we also have recent, and for recent, we are talking about possibly 100 million years old, other type of faults, and so all together interacting and exploiting each other's existence, generating moonquakes that again plausibly may have triggered this landslide. Not sure we will ever find out, but these are the two competing hypotheses. And from the middle, from the center of the light mantle deposit, the location called Station 3, the astronauts extracted 2 core samples. Okay, that's just a schematic representation of these 2 core samples. They use a double drive tube. They sampled down to a depth of about 70 centimeters. And those are just the thin section showing, I have another video. Shall we go? Yes. There's also maybe the audio if possible, but in case I can just talk over. So this is Gene Cernan hammering down the double drive tube, which is this tool that is now extracting and pulling out from the ground, containing the two core sample. And so NASA decided to keep them preserved, waiting for the future, and decided, okay, now we are ready to look at these samples. And so in 2019, the upper sample, 73002, was finally opened, whereas 73001, the lower sample, waited until early 2022. And here is just, okay, the sample collection was perfect, let's say. Things fell over, but still we have this material back with us, and we have just a quick look at that. And here, just to show you how, so this thing, the core on the right-hand side of the slide is a X-ray scan of the upper sample, and compared to the one next to it, to the left, that's an X-ray computer microtomography scan of the sample, so a much higher resolution. And you can really appreciate how much more we are able to see. And, oh, okay, there was another video, it's not going, but anyway, there was another really cool video going through the column, and so we could really appreciate the detail of the class. And so, I mentioned the ANXA initiative. So NASA took this opportunity to, as a testing ground to understand curation processes, because how we just discussed, sample, samples are really, really important to then understand, in this case, the moon, but wherever they come from, they're really fundamental. So, and they come from an environment that is completely different from Earth. So we don't want to contaminate the sample. So the curation process is really fundamental. And so looking forward to future mission that will bring a sample from other location, that was really, there were a lot of lessons learned from the ANXA initiative. And here are just few pictures of the team, the curation team, and in the lower left photo, they're handling the lower sample. And here instead is an image of the extruded. It's probably the upper one. And the way have been, yeah, didn't mention, these samples don't exist anymore. They have been, well, let's say destroyed, but extruded for analysis. And so also the scanning of the sample is really providing a really precious digital reference of the sample itself. And so it can still use for studying, despite the fact the physical sample doesn't exist anymore. And here are other images of the sample. It was not just about curation processes that were learned during this initiative. It was also how to safely extract the sample from their vacuum containers, so without contaminating the sample. And so, I'm not sure how much we have left. I'm probably overrunning, so I will try to go quickly. So we have been talking about the past and the present, and so the question is what's next? Where are we going next? So that's just a timeline of the successful mission to the moon, a mix of lander, hard lander, soft lander, and orbiters and flybyers. And so we really need to go and sample other places. There was another video. Anyway, it was quite cool. Anyway, so imagine now there's a rotation and we're approaching the South Pole. And that's where the next mission are going. Why we are going there? Because from orbit, we realize that the moon has, let's say, a lot of water. Again, it's not liquid water in terms of molecular water. So again, in terms of, in the form of hydrogen molecule or the H molecule attached to the mineral structure, okay? And so it's there, and it would be really interesting to go and sample some of these places. That moved, okay, it goes. Okay, that will be quick. And why we go there? Also because for the, let's say, geometry between the poles and the sun, the sun rays, let's say, several locations where almost all the time we have sunlight that lit by the sun, and that's really, really important, because then you can just go about with your tools and solar panel. Instead, if you then pass from day and night, you really need to survive to really low temperature of the lunar night, and it's also really difficult to handle both extreme. And so that's the South. Well, the South Pole is up there. And this is called the South Pole Aitken Basin. This is about 2,500 kilometers across, and it's one of the most ancient and biggest impact basin in the solar system. And so this is an area, this is a region where very ancient rocks are expected. And so first of all, it's a location of interest because of this reason. I mentioned there could be places with a lot of sun, so be easier for space instrumentation. But we also have instead permanently shadowed regions. So there are craters but the sun never arrives. So these are called cold traps, and that's where the water molecule are expected to be trapped. They actually have been, let's say, seen from orbital imagery. And so it's the idea of going there, not just to learn about this volatile, how this water molecule happened to be in the lunar rocks, but also in terms of having long-term lunar bases for human exploration. This could be really, really important to understand how we can exploit in situ material, so we don't have to carry fuel or water with us, and can be done here. And with that, I'm done. Thank you so much for listening.
That was absolutely brilliant. I hope you agree. I think we have a question online, but any questions from you here in the audience? Yes. If we could just wait for a microphone to come round so that people online can hear you.
Thank you for a great lecture. When you've been in the lab in America analysing the moon rocks and dust, when it's in the secure environment and you've got your hands through the gloves analysing it, what happens to the dust and rock after you've analysed it?
Okay, I just want to say as a disclaimer, unfortunately, I didn't work on the sample in the glove box, but I work on the digital data set. I really would have loved to, but so the samples were then handled in, it's called the glove box, and it's stayed in say inner conditions. So you have this box filled with nitrogen, so nitrogen doesn't really react with anything, and in a vacuum too. Well, no, it's not a vacuum, it's full with nitrogen. Forget what I said. But yeah, so the curator were really careful in the way they were handling the material. And so we're careful not to lose anything. There were, to my knowledge, there was no, let's say, dust being mobilized from the sample. They were classed going from less than, I don't know, around 0.15, if not smaller, millimeter, up to a couple of centimeters. But yeah, and they're all now, being separated and classified by size range like that. But yeah, everything is done in extremely clean conditioning and control condition.
So we have a question from online. Is there a plan to establish more geologists on the surface of the moon? Also, what kind of structures will the base have? Will it be a dome on the surface or underground facility?
Okay, cool. I'm going to start from geologist. Unfortunately, I didn't sign up for becoming an astronaut. I'm not a big fan of rockets, but of the, recently, it is now a few years, NASA has selected the next generation of astronauts. And amongst them, there's a geologist. She's a geologist, graduated from UCLA, and she's amazing. She's my favorite, and I'm really rooting for her to be the first woman, and actually also first person of color to go to the moon. So that's the only geologist, but compared to the Apollo, let's say, range of and variety of profession. So the Apollo were mainly test pilots from the military, and this time NASA has selected a range of profession, walk of path. vocal life. Yes. So from biologists, from a surgeon, and also, yes, just one geologist, but it's good. So hopefully, yeah, the tradition of geologists to the moon is in really, really good hand. And about the lunar base, so I guess maybe all of us have seen some of this illustration of what to expect as a moon base, and we tend to think about domes. But the problem of that is building the thing. So we need to bring material with us, and that costs money. So possibly it could be like exploiting either the material there, or I mentioned lava tube, but unfortunately that collapsed. But lava tube are empty space basically in the lunar underground, and they could really be interesting places to explore, to exploit as lunar bases, because they will first of all protect us from the harsh lunar environment, so cosmic radiation and maybe meteorite bombardment. But we also need to be careful they won't collapse. But that could be an option. Yeah.
First, thanks for great presentation. I just wonder, now we can say Earth gravity like 6 times than moon gravity, and you can say and we can see some landslide from there, and Earth like similar, we can say maybe, and we can say like some of the rock types, they are same, like basalt and granite and other things. Can we say they are affected from same magnetic fields? Because already if there is like earthquake and other things, there depends of magnetic fields. Can we say Earth and Moon, both, they affecting similar like cosmetic things?
Okay. Again, another disclaimer, I'm not a big expert about magnetism, but my understanding, and if someone knows better, please help me with this. My current understanding is that the moon doesn't have a magnetic field at the moment. That's my understanding. And so if it had, it was in the past. And so, I don't know. Well, you know what? It's our neighbor. We are really close together. So in a way, we can expect that what affect the Earth affect the moon too, and vice versa. And so in a way, yes, studying things on the moon that we cannot on our planet because of, it's a we don't have a record of ancient rocks on Earth anymore because of active tectonics, or because we have an atmosphere protecting us. Then we need to rely on studying the geology on the moon to understand these processes. And we can, to some extent, draw this parallelism. And so expecting that what happened on the moon happened on Earth as well. I'm not sure if I answer to your questions, but yeah.
Yeah, I just like, I try to understand something about the moon and Earth, because already we have some HO2, like water as well, and we can see some like clay, there is like, Earth one, I think is similar chemical formulas.
Yes,
yeah.
There would be, the difference would be in, let's say, a geochemical signature, probably. So in some type of isotopes, for example, present in the minerals, and but also maybe in the relative abundance of some element compared to others. For example, if I'm not wrong, I mentioned titanium-rich volcanic glass beads, and so there are some of the basaltic rock rich in titanium, which is my understanding is not common or what we see also on Earth. So there are differences, and even if there are not similarity, but differences are also really important to understand these processes and how different planetary bodies can take different routes, and understanding why. And this is for us and the Moon, but it could also be for Mars or Venus, which is like almost same size as Earth, and why those two planets took completely different climatic paths. This is climate, but it can be like geology. So even differences are really important to better understand the whole picture.
Thank you.
There was also
Thank you very much. Great talk. Quick question, please. So the Earth with its plate tectonics, I think, gives us earthquakes. I'm not a geologist, just a member of the public. Why do we get moonquakes? What causes that?
Okay, so yes. So one possibility, although for someone is a bit strange, it would be that the Moon is still contracting from cooling. But this doesn't really fit the understanding of how quickly planetary bodies cool, because then, let's say, the larger is a planet, the longer it will take the nucleus, the interior, to cool down. Okay, so the Moon is much smaller, so we would expect it to cool much faster. And so with that expectation, quakes from the contraction of the Moon, so fault, shortening the crust, are something that still, like, people think, we are not really sure that was happening unless we don't know some sort heat source present deep in the lunar mantle, maybe from still radioactive decay, and so still providing then heat, and so then as a consequence cooling possibly. But then for sure we have the tidal forces. So it's the tidal interaction with the Earth, so the Earth pulling. And the Moon is just, so we see just one face of the Moon. So one face is always facing us, and so, I need to use my hand. And so it's this pulling, from this tidal interaction, so gravitational interaction, that for sure is generating some of these tremors. Maybe some of the deepest quakes. And yes, so let's say this would be for quakes associated with fault. Then we have quakes that comes from impact cratering. So bang, a big bang, shaking things. So that could be also a reason for generating boulder falls or landslides, or we don't necessarily need, let's say, seismic activity. But yeah, that's two options at least on the table. Yeah.
I think we have a question at the front, and then maybe one more question after that.
Great talk, thank you very much. You were talking about, or someone asked about habitats on the Moon, and linked in with something else you said about the fact that it would be very difficult to transport everything you need from Earth to the Moon to make habitats. I remember reading somewhere a while ago that they were talking about using 3D printers and using the regolith to create habitats as well as other things that they may need on the Moon. How does that fit in with what you were saying about the fact that regolith is so fine that you don't want to get mixed in with your equipment and you don't want to breathe it in? Obviously, you're not going to be just breathing without a spacesuit on the Moon, but how do those two things go together? It seems a slight conflict.
Yeah, there's a lot going on in trying to understand in situ resources, so the regolith, how the regolith behave. And so the regolith, okay, I mentioned the most annoying part of the regolith, which is the extremely fine particles. But the regolith is also made of a wide range of sizes, so centimeters in diameter class or so. So I guess it would be a matter of really understanding how to exploit the regolith. And so find a way either to discard the finest, most annoying bit if we don't manage to put it together to create a material suitable for 3D printing. That's it. But yeah, but I think it's probably the way to go. So in a way, it's not that it's impossible to bring, let's say, our material from here. It would be just really expensive, really expensive. It would be more journey, more fuel, because spacecraft is heavier. So 3D printing, I think it would be a really cool option. And yeah, and I think they have been experimenting 3D printing in space, in the International Space Station. And that has been serving to really study, this alternative from, and also human physiology, because you mentioned the harsh environment. And another thing is that how are we going to enjoy that harsh environment? So yeah, no.
Have you ever looked at the Apollo missions list and wondered why it starts at Apollo 4? Or if you're not an epic space nerd, did you know that the first flown Apollo mission was Apollo 4? So what exactly happened to Apollos 2 and 3?
2, 1, we have a liftoff, 32 minutes past the hour.
Hi everyone, I'm Amy. This is The Vintage Space, my little corner of the internet where we talk about all things mid-century that I love, and a lot of that happens to be Apollo-era spaceflight. This is something maybe really obscure that you've never noticed or thought about. The Apollo missions go from the tragedy of the Apollo 1 fire to Apollo 4 without any mention of Apollos 2 or 3. It's actually a pretty interesting story, albeit a really inside baseball kind of nerdy story, about how mission naming conventions worked in the early space age. The Saturn V that launched the Apollo missions to the moon was part of the Saturn family of rockets, the Saturn I, the Saturn 1B, and the Saturn V. Of course, there's more to these rockets than just stages, but this gives us a good sense of how they fit together as a family. The Saturn I was the smallest in the family. It used an S1 first stage manufactured by Chrysler. The bulk of this stage was the cluster of 9 propellant tanks, 1 larger internal tank and 8 surrounding it. These tanks fed a mixture of RP-1, or Rocket Propellant 1, and liquid oxygen to the 8 H-1 engines that got the rocket off the ground. The second stage was an S-4 built by the Douglas Aircraft Company, powered by 6 Pratt & Whitney RL-10 engines burning a mix of liquid hydrogen and liquid oxygen. Next in the series was the Saturn 1B. This rocket was the same as the Saturn I, but with the more powerful S-4B upper stage. It still used liquid hydrogen and liquid oxygen, but instead of the 6 Pratt & Whitney engines, the S-4B used a single J2 engine. The Saturn V represented the most powerful rocket in the series. Where the previous rockets used 2 stages, this one used 3. The Boeing-built S-1C first stage used RP-1 and liquid oxygen to power the 5 F-1 engines. The S-2 second stage, built by North American Space Division, used 5 liquid oxygen and liquid hydrogen-powered J2 engines. The third S-4B stage was the same as the upper stage of the Saturn 1B. NASA started Saturn I launches in 1961 with boilerplate Apollo spacecraft and ballast payloads to study the rocket's development and later the spacecraft's development. And right off the bat, the agency used a straightforward naming scheme, a letter denoting the rocket and test type and a number denoting the specific launch. There were 10 Saturn I launches labeled SA for Saturn Apollo or AS for Apollo Saturn, followed by the number. Whichever letter came first was the emphasis of a specific test. The serial numbers or internal designations for Saturn I missions went from SA1 to 10, but the missions were a little different. SA1 through 5 were rocket development tests. Then the designation changed to the 100 series numbers, marking the shift into Apollo tests. AS-101 to 105 were the first Apollo hardware launches. There were some other tests early in Apollo's development that used a different but still consistent designation. Hardware tests using a Little Joe rocket were labeled A. A1 through 4 were these Apollo hardware tests. As Apollo advanced towards manned missions, NASA began using the uprated Saturn 1B. These missions had the internal designation of SA for Saturn Apollo, but their mission numbers used AS for Apollo Saturn, followed by a 200 series number. The 200 series was reserved for the Saturn 1B. 3 Saturn 1B tests launched in 1966 while the interim Gemini program was coming to a close. AS-201 launched on February 26th as a suborbital test of the Saturn 1B and a Block 1 Apollo command module as its payload. AS-203 on July 5th was another suborbital flight to test the command module's heat shield. AS-202 was a test of the Saturn 1B rocket. The next mission in the Saturn 1B sequence, AS-204, was a simple but vital Earth orbital test of a Block 1 command module with a crew, scheduled to launch on February 21st of 1967. When the spacecraft for the AS-204 mission, Spacecraft 12, arrived at the Kennedy Space Center on August 26, 1966, it was protected by a cover emblazoned with Apollo 1 in capital letters. The mission was publicly known as Apollo 1, the first in the series of manned missions that would culminate in the lunar landing. From here, NASA's plan was to have Apollo 2 launch on a duplicate of Apollo 1's mission to gather additional data from the relative safety of Earth orbit. Even though the Block 1 model couldn't support the lunar mission, only the Block 2 could dock with the lunar module and thus support the lunar landing mission. I have a whole video on why NASA built 2 versions of the Apollo spacecraft right up here. Apollo 3 would then debut the advanced lunar-capable Block 2 command module. But it wasn't long before this plan fell apart. Spacecraft 14, the spacecraft for Apollo 2, was badly behind schedule, and many within NASA began questioning the value of a second Block 1 mission. Not to mention the agency had abandoned the practice of duplicating flights after Gus Grissom repeated Al Shepard's suborbital mission in 1961. The standard practice had become to take steps forward and achieve a new goal with every flight. Not long after the final Gemini mission splashed down on November 15th of 1966, George Miller of the Office of Manned Spaceflight canceled Apollo 2. The missions were reorganized, so Apollo 2 would now debut the lunar module on another Saturn 1B flight, and Apollo 3, a high Earth orbit mission with both the command and lunar modules, would also be the first manned Saturn V flight. This was the standing order for Apollo missions at the beginning of 1967, and each had an assigned crew already in training. Then NASA was struck with its first major setback. During a routine pre-launch test, a fire ripped through the spacecraft 12 and killed the Apollo 1 crew. The ensuing accident investigation revealed flaws in management practices and fundamental issues in the spacecraft's overall design. The review board recommended dozens of changes to the spacecraft. NASA and the command module prime contractor North American Aviation were facing substantial redesigns, which promised to delay the whole program. The fire also forced Apollo management to reconsider its mission schedule. The question became whether it was worth launching the Apollo Block 1 flights at all. With so many changes pending, was there anything really to gain from launching a version of the spacecraft that couldn't go to the moon? Towards the end of April, the decision was made to cancel all manned Block 1 flights, and with the lunar module also behind schedule, Apollo missions would start with an Earth orbital Block 2 command module only flight, followed, possibly, by a lunar orbital command module only flight. Reassessing the Apollo schedule brought a change in naming conventions. The widows of the Apollo 1 crew asked that NASA retire the mission designation in honor of their husbands. Moving forward from here, NASA had 2 options, both of which George Miller outlined in a letter to George Low, Deputy Director of the Manned Spaceflight Center. The agency could proceed in sequence and name the first mission after the fire Apollo 2. Or it could count the unmanned Saturn 1B test flights as part of the Apollo series and retroactively rename them to have sequential Apollo designations. AS-201 would become Apollo 1A, AS-202 would become Apollo 2, and AS-203 would become Apollo 3. This meant subsequent flights following the fire would begin with Apollo 4. On April 24, 1967, NASA's Office of Manned Spaceflight announced that AS-204 would officially be recorded as Apollo 1. AS-201, 202, and 203 wouldn't be renumbered in the Apollo series, but subsequent missions would be named, beginning with Apollo 4. Apollo 4 marked the first Saturn V flight and brought with it a new naming scheme. Internally, the missions were denoted SA for Saturn Apollo and given a 500 series number. SA 501 was publicly known as Apollo 4, and it launched on November 9, 1967, with a Block 1 command module with Block 2 elements installed as a spacecraft and rocket test. Apollo 5 launched on the Saturn 1B intended for the Apollo 1 mission on January 22, 1968, so was known internally by the same designation, AS-204. But its alternate notation of SA-204/LM1 speaks to its goal of the first test flight of the lunar module's ascent and descent engines. Since it was only an engine test, it didn't even fly with legs. Apollo 6, internally AS-502, was another Saturn V test flight with a modified Block 2 command module and a lunar module test article. Apollo 7, internally AS-205, was the first manned Apollo mission. It launched a Block 2 command module on a Saturn 1B into Earth orbit on October 11, 1968, doing what Apollo 1 had intended more than a year and a half earlier. It was the flight that got Apollo back on track, and the familiar, steady sequence of missions from this point on points to the program's success. Apollos 8 through 17 had the internal sequential designations of SA-503 to SA-512. SA-513, originally earmarked as the launch vehicle for Apollo 18, was the final Saturn V to fly, only instead of going to the moon, it launched the Skylab space station into orbit. SA-514 and 515 were two unused Saturn Vs intended for Apollos 19 and 20. The pieces are now on display at the Johnson and Kennedy Space Center as part of full Saturn Vs. To finish out the Saturn 1B story, SA-206, 207, and 208 were the three Skylab missions, and SA-210 was used for the Apollo-Soyuz test program. SA-209 and 211 were built but never used, and SA-212, 213, and 214 were built in part before being scrapped. I hope that little weird insight into Apollo naming conventions and mission numbering answered a question some of you guys didn't even know you had about the lunar program. Or maybe it just gave you good fodder for your next cocktail party chat. What if Apollo hadn't been cancelled? What would those last missions look like? When Richard Nixon took office in 1969, Apollo had missions on the books through to Apollo 20. And of course, only 17 missions flew. After Apollo 17, there were no more trips to the moon. But do we know what those missions would have looked like? Maybe. The crew element of this is easier to go through because there was a very regular way that Deke Slayton, who was head of the astronaut office, would pick crews. He basically did it on a cycle. A crew would be the backup crew for one mission, then sit out 2 missions, and then would be the prime crew on the 3rd round. So based on the backup crews, we can figure out what the last 3 Apollo missions would have looked like. Apollo 18 would have been commanded by Dick Gordon, who was the command module pilot on Apollo 12. He would have flown with Vance Brand and Jack Schmitt. Jack Schmitt was ultimately actually moved to the crew of Apollo 17 because he was a trained geologist and NASA wanted at least one trained scientist to go to the moon. Apollo 19 would have been commanded by Apollo 13's Fred Hayes with Bill Pogue and Jerry Carr. Apollo 20 would have been a second lunar mission for Pete Conrad with Paul Weitz and Jack Luzma as his crew. These missions were all initially on the books as J missions, which meant they were longer stays and would have used the lunar rover to cover more ground. It's a little bit harder to speculate on where they would have landed, but we can look at the list of initial sites that NASA wanted and look at the ones that didn't have missions. Copernicus, Tycho, Marius Hills, and Sensorius were all places that NASA was interested in, but never actually sent a mission. Apollo 20 was the first to get the axe. The Saturn V from that mission was then moved over to the Skylab program to launch the space station. In September of 1970, kind of because he was spooked by the near disaster of Apollo 13, Nixon canceled 2 more Apollo missions, Apollos 15 and 19. What this means is he was canceling one of the medium-stay H missions and a longer-term J mission, such that the last 3 missions, 15, 16, and 17, would be the long-stay J missions with the lunar rover. The rookie astronauts from those canceled Apollo missions ended up flying on Skylab and into the shuttle program, and Pete Conrad did command the first Skylab mission as well. Dick Gordon and Fred Hayes, though, never flew in space again.
arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, copper, copper, tungsten, tin, and sodium. But now we've got lawrencium, meitnerium, darmstadtium, seaborgium, brongenium, and dubnium, flerovium, and borium, copernicium, livermorium, and hassium, rutherfordium, organocin, and tennessine, muscovium, nihonium. Of course, this doesn't mean that the periodic table is finished. Some more elements may yet be discovered, or more accurately, synthesized for a fraction of a second in a laboratory. But don't worry, we've got that covered. I'd like to add those elements which one day may be discovered. But it took so long to learn the song, I really can't be bothered. Antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, copper, tungsten, tin, and sodium. But now we've got lawrencium, meitnerium, darmstadtium, seaborgium, brongenium, and dubnium, flerovium, and borium, copernicium, livermorium, and hassium, rutherfordium, organocin, and tennessine, muscovium, nihonium. Of course, more elements of the periodic table may yet be discovered, or more accurately synthesized for a fraction of a second in a laboratory. Don't worry, I've got that covered. I'd like to add those elements which one day may be discovered. But it took so long to learn this song, I really can't be bothered.
And with that, we'll close the meeting and hopefully we'll see you at the September meeting, everyone. Thank you.